The universe stretches out before us, vast, mysterious, filled with wonders beyond our wildest imaginings. We gaze at the star-dusted canvas of the night sky and ponder our place within this cosmic ballet. What fundamental rules govern all that we see, and more intriguingly, all that remains unseen? Our relentless quest for answers propels us to the very edge of understanding. Imagine a reality far stranger than any tale spun by science fiction. Picture a domain where tiny particles can exist in multiple places simultaneously, where they can seemingly communicate across vast cosmic distances faster than the speed of light itself. This is the quantum world. It forms the very bedrock of our existence, yet remains shrouded in profound mystery. A grand cosmic puzzle, its pieces scattered, waiting for us to assemble them. Each new discovery only reveals deeper, more perplexing questions. We are explorers, navigators on an infinite ocean of discovery. The universe whispers its secrets to those who dare to listen intently. Sometimes these whispers are faint, almost imperceptible, but they hint at an underlying order, a hidden interconnectedness that binds everything. A magnificent tapestry woven with threads of energy and information. These threads are unseen by the naked eye, yet profoundly influential. The search for these threads is our great adventure. This journey into the quantum realm is not merely an academic pursuit. It is fundamentally about understanding ourselves and our role in this vast, interconnected cosmos. Consider two infinitesimally small particles born from the same event. Like identical twins, they share a common origin. Now, let us separate these twin particles across the cosmos. According to classical reasoning, they are now independent entities. But the quantum world subverts our intuition. These particles, if entangled, remain mysteriously linked. Measure a property of one particle, and you instantly know the corresponding property of its distant twin. This is quantum entanglement. Albert Einstein referred to this phenomenon as spooky action at a distance. It appeared to violate the cosmic speed limit, the speed of light, yet experiment after experiment has confirmed its undeniable reality. Entanglement is a fundamental feature of the universe. It hints at a deeper, more fundamental level of existence, a cosmic secret whispered by the quantum realm. The story of quantum mechanics is a human story. Brilliant minds wrestling with the universe's most profound secrets. At the dawn of the 20th century, classical ideas were failing. Max Planck proposed that energy comes in discrete packets or quanta. This ignited the quantum revolution. Albert Einstein used Planck's idea to explain the photoelectric effect, proposing that light behaves as particles' photons. Niels Bohr applied these ideas to the atom, envisioning electrons in quantized energy levels. Werner Heisenberg introduced the uncertainty principle. You cannot simultaneously know a particle's exact position and momentum. Erwin Schrödinger developed wave mechanics, describing particles as waves of probability. These pioneers often disagreed, engaging in fierce debates. The intellectual duels between Einstein and Bohr are legendary. Einstein searched for a deterministic reality, while Bohr embraced the probabilistic nature of the quantum world. Their struggle profoundly shaped our understanding. It pushed the boundaries of what humanity thought was possible to know. Imagine an experiment, firing tiny bullets at a barrier with two narrow slits. On a detector screen behind the barrier, you expect to see two distinct bands. This is classical behavior. Now, let us journey to the quantum realm. Instead of bullets, we use electrons. Fire these electrons one by one at the same barrier. Instead of two bands, an interference pattern appears. This pattern is the hallmark of waves. Each electron behaves as if it passes through both slits simultaneously. It transforms into a wave, exploring all possible paths. Then, it interferes with itself before collapsing back into a particle. This wave-particle duality is a central mystery of quantum mechanics, but the mystery deepens further. Place a detector at the slits to observe the electron's path. The interference pattern vanishes. The act of measurement forces the electron to choose a single slit. It behaves like a well-defined particle again. The universe itself seems to know when we are looking. This challenges our most basic understanding of reality. The quantum world is a place of profound and unsettling paradox. It lies at the very heart of quantum mechanics. We return to the enigmatic entangled particles. Albert Einstein, Boris Podolsky and Nathan Rosen devised the EPR paradox. They argued that quantum mechanics could not be the whole story. There must be hidden variables explaining the particle's behavior. John Bell devised Bell's theorem to test these ideas. If the universe operated according to hidden variables, certain measurements would obey Bell's inequality. If quantum mechanics was correct, this inequality would be violated. Experiments were carried out by physicists like Alain Aspect and John Clauser. The results consistently violated Bell's inequality. The universe is indeed as spooky as quantum mechanics predicted. This means there are no predetermined local hidden variables. The properties of entangled particles are not fixed until measured. Bell's theorem solidified entanglement as a fundamental feature of our cosmos, a profound truth whose full implications we are still grappling with today. The debate continues with vigor. Imagine throwing a ball at a solid wall. The ball bounces back, unable to break through. This is our everyday experience. But in the quantum realm, particles can pass through energy barriers. This phenomenon is known as quantum tunneling. Particles perform a seemingly impossible feat. They pass directly through barriers without enough energy to overcome them. Quantum particles exhibit wave-particle duality. Their probability wave decays as it penetrates the barrier. A tiny part of the wave can extend through the barrier. If the barrier is thin, the particle appears on the other side. Quantum tunneling is essential for life as we know it. The sun shines because of quantum tunneling. Protons in the sun's core fuse together, releasing energy. They tunnel through the repulsive energy barrier, allowing nuclear fusion to ignite the stars. Quantum tunneling powers our world. Erwin Schrödinger devised a thought experiment to illustrate quantum superposition. Imagine a cat in a sealed box with a radioactive atom. If the atom decays, the cat dies. If not, the cat lives. Until we observe, the atom is both decayed and not decayed. The cat is both alive and dead. This paradox highlights the problem of how quantum rules transition to classical rules. Observation collapses the superposition into one definite state. The measurement problem remains one of quantum mechanics' deepest mysteries. The quantum eraser experiment extends this theme. If we erase which slit information after the particle has passed, the interference pattern is restored. It is as if a choice in the present influences the past. Causality becomes fuzzy, perhaps even illusory. The quantum world is a place of profound and unsettling paradox. It challenges our very notion of an objective reality. Quantum mechanics works. Its equations form the bedrock of modern technology. But what does it all mean? Physicists have proposed many interpretations. The Copenhagen interpretation suggests properties are undefined until measured. Measurement collapses the wave function into one state. It accepts the probabilistic nature of quantum events. The many worlds interpretation posits that every quantum event causes the universe to split. One universe for each possible outcome. We experience only one branch. This avoids the problematic collapse, but suggests infinite parallel worlds. Bohmian mechanics suggests particles have definite positions guided by a quantum wave. Other interpretations offer different philosophical lenses. No single interpretation has been definitively proven. The debate continues with vigor. The true nature of quantum reality remains an open question, a vast frontier for future generations of explorers. Quantum mechanics compels us to rethink our most fundamental concepts. Our place in the universe. The mystery deepens with every new insight. The dance of quantum particles is becoming the engine of a new technological revolution. Quantum computing holds the potential to solve complex problems, simulating molecules for drug discovery, designing revolutionary new materials, breaking sophisticated encryption codes, creating unbreakable quantum cryptography. Quantum computers harness superposition and entanglement. The future is quantum. Quantum sensors promise unprecedented precision, detecting minute variations in gravitational fields, revolutionizing geology, resource exploration and navigation, improving medical imaging techniques. Quantum communication offers perfectly secure channels. These technologies are emerging from research laboratories. Quantum mechanics compels us to rethink our place in the universe. If observation influences reality, what does this imply about consciousness? Are we passive observers or active participants in the universe's unfolding? The mystery deepens with every new result. We are stardust, animated by quantum laws. Our epic journey of discovery has just begun.